Hey folks, this is Major Jones here to talk to you about performance improvements that we get with our pipelines. So we've kind of alluded to this in so far in this unit 5, that we do get performance improvements from our pipelines, and we've kind of discussed a little bit of the theoretical improvements. In this lesson, what I want to do is review the performance equation for our computer and using some actual values determine what is the actual numerical performance improvement we get with pipelining our LC3 over whatever the version we had in Unit 4 was. After comparing those, we're going to understand what actual improvement we get from our pipeline and what sorts of things affect the improvement that we get based on how we've kind of designed our pipeline. And additionally, I want to introduce to you 2 industry standards that I use today to compare the performance between processors. So let's get started. To begin with, I'll remind you that performance typically means faster is better. There are lots of different ways we can compare computers based on how much power they use or which specific tasks they're better suited for. But at least in this class, we'll define performance in terms of execution time. So you can see that kind of summarized down here in my performance equation. If I've got a computer which can run a specific program with a smaller execution time, and that performance goes up, okay? And so the execution time is a function of 3 factors, which are the number of actual machine instructions that are in my program, how many clock cycles it takes to complete each of those instructions. CPI, recall, is clock cycles per instruction. And how long it takes my processor to complete 1 clock cycle, otherwise known as the cycle time, right? The period of the clock. And if we multiply all these together, then we get a value which is in units of seconds that reflects exactly how long it should take this processor to run a specific program. And if between 2 computers, one of them can run the exact same program in less time, then that computer is said to have better performance. The period of the clock can, of course, also be known as, or it can be described as the frequency. We can put that in the numerator if that's the case. And I think it's interesting to note then that the 2 terms that are left here in the denominator, instructions per program times clock cycles per instruction, are effectively a measure of the total number of clock cycles that it takes to run our program. We'll use that kind of simplification here in a second when we credit computer performance. And I feel like it's a useful kind of heuristic to help understand what's going on in this equation, right? So, if we figure out what are the total number of clock cycles that it takes to run our program, and we know, how many clock cycles we can execute in a given second, then these 2 terms, tell us our performance, okay? So we're going to use that equation and some given values here to compare the performance between our pipeline processor, the one we sort of developed conceptually here in Unit 5, with our non-pipeline processor from Unit 4. And this is also known as a multi-cycle kind of non-pipeline processor to describe the fact that the way this non-pipeline processor executes is with that big state diagram, right? Where we have on each clock cycle, we're transitioning from one state to the next. So there are multiple states and multiple clock cycles that are used or that transpire in the execution of each instruction before we come back around to the top of our fetch phase. To compare these 2, we're going to need a program to be used as a sort of our benchmark. So we'll use this program right here. This is a rehashing of our multiplication program. So you can see here I'm loading 2 values into R0 and R1. I'm jumping to the multiplication subroutine. I'm doing the process where I repeatedly add into a register in order to simulate the multiplication, and then I return from my subroutine. You can ignore the red ink for right now. We'll get to that later. Additionally, I need to figure out, make some assumptions as to the how long each sort of process takes in each clock cycle takes in my processor. So we'll use these values to sort of estimate the latencies in our system. We need to make some approximations because these latencies, these dummy values are kind of they're associated with, or they're more from the viewpoint of the actual pipeline processor. So we'll need to make a kind of a couple of assumptions in our calculation for the performance of at least our multi-cycle processor. Right. So to do that, right, we're going to apply our performance equation. We're going to start with our period or frequency of our clock, and that's limited by the single longest stage in our finite state machine. Based on my inspection, so this is, I was looking at the finite state machine diagram here. Based on my inspection, the longest single stage is either this one or one of these ALU operations here. Like I said, if we're using these values down here, we don't exactly have data on how long like each of these fetch cycles take. We'll kind of hand wave a little bit by saying these first 5 stages, that's just the fetch phase. Anywhere down here where we are like computing a PC offset, that's going to be like the evaluate address stage. Okay. In the case of the ALU operations here and add a not, we're kind of doing 3 stages in one clock cycle. We are reading from our source registers, we are using the ALU to perform an operation, and then we are also writing that value back into the destination register. So by my math, and it may not be super nice to the multi-cycle processor, we have to add up the latencies from those 3 stages to get what is sort of the longest delay. So if we look at the data down here, based on these values, right, it takes 350 picoseconds to read from the registers, 150 picoseconds to use the ALU, 200 picoseconds to write back into the register file. By my calculation, right, that means that that one stage takes 700 picoseconds, and unless I'm mistaken, that's the longest one in our state diagram, so that becomes the limiting factor in how quickly we can run our clock. So cycle time is 700 picoseconds. The program here on the right has 21 instructions. So that's the number of instructions we're trying to execute. And the last thing we need to figure out our performance is to compute how many clock cycles these instructions take. Again, we have to kind of approximate here because these stages don't map perfectly to our finite state machine, but we'll do our best. So what we can see from, if we take a look at that state diagram is, like we saw before, our and our add instructions, they take 2 clock cycles because we're fetching on 1 clock cycle and we're performing, all 3 of these read register, ALU, and write register on the 2nd clock cycle. Similarly, like our JSR and our return instructions take 2 clock cycles because on the first, effectively, they're fetching an instruction. On the second, effectively, they're evaluating an address or reading from a register and then updating the program counter and going back to the top of the fetch phase. So that's basically 2 kind of stages, 2 clock cycles. On the other end of the spectrum, we've got a load instruction that, by my count, takes 4 clock cycles. And that's because on 1 clock cycle, we're going to fetch the actual load instruction. On the next clock cycle, we're going to evaluate the address. On the one after that, we're going to access memory. And then lastly, we're going to write to a register. So what you can see here is me computing what are the total number of clock cycles then for this program. So, with 3 load instructions, if each one takes 4 clock cycles, that's 12 clock cycles that occur from the load instructions. If I've got 9 add instructions and each one takes 2 clock cycles, then I've got another 18 clock cycles that occur based on the add instructions here. And of course, I'm including in this actual program the fact that we're looping here. So that's why I've got 9 add instructions, because these 2 add instructions occur multiple times. And if I do that for each instruction in this program, what I get is that there are 50 clock cycles that occur in the execution of this specific program from the first instruction here, loading R0, right up until my LC3 completes the return instruction and sort of stops right here at the halt. We'll not include the halt just for the time being. And so if I calculate that right, 1 over 700 picoseconds divided by 21 times 50 clock cycles, I get the value 28.6 million inverse seconds. And all that means is that in this version of the LC3, as long as I've done my math sort of correctly, these approximations are accurate, then this version of the LC3 should be able to execute this program almost 29 million times every second. Okay, that's the performance of this LC3. All right. So let's try to compare that with our pipeline version. All right, so a little shorthand here, right? I've got the stages to my pipeline, so what we're going to do is follow the same process, but using that as the underlying processor. Now, in this case of my pipeline processor, my longest single stage is the read register stage, And it's just that one that is sort of limiting how quickly my clock cycle can run. And so my cycle time is just 350 picoseconds from that one sort of single longest stage. In order to compute the number of cycles that it takes to execute my program, I have to first account for the 4 clock cycles it takes to sort of fill my pipeline. And then after that, I should get one instruction on every clock cycle, except in the case where I have hazards. And so now it's important that we take a look at this ink in red here. You can see here I've annotated each of my control hazards and each of my data hazards. I've got one data hazard here, which incurs a 3-cycle penalty. One data hazard here, which incurs another 3-cycle penalty. I'm assuming in this stage, or at this point, we're using sort of the strategies from the must-do lessons. So for the data hazards, I just have to stall until the data hazard is resolved. And you can see I've got a number of control hazards since I issue a JSR instruction. I've got a branch instruction down here and a return instruction. I'm going to use the control hazard strategy where I assume a branch is not taken, unless it is, in which I flush the pipeline. And so what that does is, gives me a 3-cycle penalty from many of these jump instructions. But I managed to save a couple of clock cycles here on the very last iteration when I managed to predict correctly that this branch is not taken. But all told, that means that in addition to the 21 instructions that I need to execute in my base program, I've got another 21 no-ops that my pipeline issues in order to resolve the data and the control hazards. So if I make that calculation, right, 1 over 350 picoseconds divided by 42 instructions plus 4, so 46 total instructions, I get the value 68 million inverse seconds. What that means is my pipeline LC3 should be able to execute this exact program 68 million times a second, which is definitely a performance improvement. The ratio of these two is 2.38 times. So what I've effectively shown is that my pipeline processor, at least in the case of this specific program, can run almost 2.5 times faster than my multi-cycle processor. Which is definitely a performance improvement, although it's not quite the performance improvement we would have expected from our pipeline processor. The reason for that kind of comes down to these no-ops, right? We would have expected maybe something a little closer to a 5 times performance improvement, at least theoretically. But given this exact program, I'm executing as many no-op instructions as I am actual instructions in my processor. And that really kind of degrades my performance. So step number 1, right, was to kind of review the performance equation, look at some numbers for our actual 2 processors and get a feel for what their actual performance is. The second thing I wanted to talk about is what factors are affecting these 2 performance values, and what are some ways we might be able to sort of try to get a better performance out of our LC3. The base program, the one that we're running here, that we're using to compare the performance of our 2 processors, is a function of a couple of things. Firstly, what's the instruction set architecture available to us? In other words, what are some, the instructions that we can use to program in? And secondly, how good is our compiler, or how good are we as programmers to utilize those instructions? So for example, if the LC3 had a multiply instruction, then I wouldn't need to execute all this code, right? This would just be, line 3 wouldn't be a service routine jump. It would be a single instruction to perform the multiplication, which is going to significantly reduce the number of instructions I have to execute on my LC3. However, to do something like that requires lots of digital logic, and what that might mean is that as I make my instruction set architecture more robust, these stages get bigger and longer to handle these more powerful instructions. So there's a bit of a cost or a performance trade-off in terms of which instructions my processor actually implements. Additionally, my base program can be made sort of more or less efficient by how well I'm able to utilize those instructions. So, me as the programmer, if I'm trying to implement a multiply operation with this service routine, this is a really inefficient way to do multiplication, especially if my numbers are very large, right? If I'm trying to multiply 1,000 times 1,000, then I effectively execute this loop 1,000 times to do that. And there are much more efficient algorithms, much more efficient ways to do the multiplication than to just sort of do repeated addition. And so, of course, if I'm able to leverage those, and if I'm able to make my code more efficient, then I can get better performance. My performance is also a function of how quickly I can run my clock cycle, right? Which is basically comes down to these delay values, these latency values for each of my stages. We've already identified one factor that affects how long these are, which is the larger my instruction set, the larger, more robust I have in terms of what my processor can do. Typically, the longer these delay values are. So that's kind of inverse relationship. It's also a factor of things like the number of pipeline stages I have and what my hazard strategy is and just how well I can design each of these stages. As I increase my number of pipeline stages, then potentially each of these sort of values gets cut down as my pipeline stages increase. Sometimes, though, if I'm implementing a really aggressive or complex hazard strategy, then I end up adding additional logic to some of these stages. So again, there's kind of a cost trade-off in terms of what the delay values are for my processor. And then additionally, you can see here that the number of no operations, at least in terms of, for a pipeline processor, is a function of also several things, right? The number and type of hazards that are in my program can affect how many no operations get inserted. What strategy I use to try to resolve my hazards affects how many no operations are in my final program. If I introduce lots of pipeline stages to try to get my delay values really small, well, then every time I have to stall my pipeline or flush my pipeline, the number of no ops is correlated to the number of pipeline stages. So then there's a sort of a negative effect on my performance in terms of number of pipeline stages. So my aim is to kind of hopefully help you understand some of the sort of multifaceted ways in which the design of the pipeline can actually affect the performance. And it's not typically a simple matter of add more stages, make the design, take less time to get better performance. A lot of times doing those things actually worsens the performance in other ways. So the actual design of a processor is a really fun kind of search through this design space to try to find the best combination of each of these things in order to get the best performance. Now, this program here that we were using to kind of benchmark these our two processors is is semi-random, right? It's just a program we decided to run out of thin air, and if we and it heavily influenced these two performance values. If we were going to compare the performance of any other processor, it really wouldn't mean much unless we were using this exact program. And so there are actually two industry standards that are used to do exactly that. So SPEC is one company, one organization that provides programs to be used as benchmarking programs for processors. You may have heard of the terms SPEC. Let's see, where is it? Oh, SPECint or SPECfloat. So these are int short for integer and float short for floating point. These are two different groups of benchmarking programs that are offered to people to help kind of evaluate the performance of their processors. So you can see here they go by these names, right? SPECint, Pearlbench, SPECint, GCC. And you can see kind of a little description of each of these programs here that are just sort of meant to be programs that are very difficult for processors to compute and have hopefully been engineered in such a way that how long it takes the processor to do them is a direct correlation of how fast they're able to execute it. So they do really difficult things like route planning and artificial intelligence. And you can get down here into the floating point programs. They're doing ray tracing and fluid dynamics and weather forecasting. So some very, very intense programs. And the result is that you can use these. These are common enough that you can typically look up SPECint and SPECfloat values for the processor that's in your laptop to get a feel for its performance as it relates to other processors that also had data from running these exact same programs. Additionally, there's another company called EEMBC, which offers a separate performance measurement called CoreMark. the basic idea is exactly the same. We're trying to provide a standard program, standard way of compiling this program into machine instructions that let us compare the performance of different processors. The biggest difference that I'm aware of is that CoreMark is oriented a little more towards smaller processors like microcontrollers. So you'll see, less of these kind of really intense kind of computing applications, and the programs here are a bit simpler, but still very applicable to processors. Additionally, EMBC offers what I think is a really interesting power benchmark. So this is a series of programs that are meant to be run on something like a microcontroller with specifications as to how it's supposed to be run, so that when you run it, you are sort of taking power measurements the whole time. And the hope is that with something like this, you can kind of more accurately compare the power usage of different processors, which for something like a microcontroller in an Internet of Things device is very important. It determines, how long it's able to run on a battery before that battery needs to be replaced. Okay, so that's all I got. Hopefully at this point you feel comfortable looking at the performance of these two processors, and you get an idea of what sorts of factors affect the performance of our two versions of the LC3. That's all I got. See you next time.